I hope that you like drawing arrows, because today is the lecture on drawing arrows. We got to the reactions mechanisms, and all these mechanisms are mostly represented in a form of so-called push arrows. So there will be a lot of neat pictures today, and I hope you will like them, as well as the chemistry behind all these things. The only thing I want to show you before we start, so here is, well, quite arbitrary resource I was able to find. I just want to show you that there's a lot of different reactions and a lot of different mechanisms, so you shouldn't think that I have collected everything. No, by no means. But I have collected some of the mechanisms that we often see in biochemistry, and that will be probably quite useful for us in the future. Uh, with that being said, let's go. I'll just check time. Good. So a few different mechanisms, and I'll try to dash through all these slides. Maybe we will leave something over the board, but let it be. So the first, a little bit of terminology. So we'll be talking often about so-called leaving groups. That's basically any group of atoms that detaches from the main substrate during a reaction step. In organic chemistry, we often demand it to take bonding electrons with it, but you see that that may depend on the context or on the book that you are reading. Here is an example of this sort of reaction. Here you already see that arrow mechanism, and these arrows, they represent movement of the electrons. So this is basically an example of a substitution reaction that we have at the CO carbon atom. So these are this is a carbonyl group. And what do we know about carbonyl group? So we know that oxygen is electronegative. So if you have carbon atom connected to the oxygen, we can draw it this way. So oxygen tries to pull electrons towards him, and thus carbon atom becomes a little bit partially charged with a plus charge. So if we have a partial plus charge, whenever we have some different molecule that has, I don't know, some minus charge, it will like to get to that atom closer, and if everything comes neatly together, some new chemical bonds may be formed, and we will get some sort of new chemical. Here is a site I will often use. I just want to show you these mechanisms in a more, let's say, evident way. I guess this one is the simplest one. So let me show you the the mechanism and what is going on, and what do all these arrows mean, and that will be already good. Okay, so here we have a reaction. So here is a carbon atom. This is a carbonyl group. On the left, you see the same reaction, just presented in a more, let's say, flat way. So this is basically how we draw it, and this is a 3D view of what we have here. Now, what's going to happen? So here you see NH3 molecule. So nitrogen has a this non-bonding electron pair, so there is some sort of negative charge. Here you see this pair presented as these two dots. You don't see that pair, but you might guess that it is localized somewhere here, so this sort of tetrahedral structure, and it will attack carbon atom of the carbonyl group. Why? Because oxygen is electronegative, it pulls electrons towards him, and carbon gets a little bit plus charge. So it's pretty reasonable to try to attack that carbon atom. And if there is no steric hindrance or some other obstacles, we can basically do that. What do we see in this picture? So we see one chemical, we see another chemical. What do these arrows show us? They show us that these electrons from these non-bonding electrons will be used to create a new chemical bond between nitrogen and carbon atom. But if that happens, you know that carbon, oxygen, nitrogen, they like to have 8 electrons around. So if it just creates this sort of bond, we will violate this rule, and it's, well, not energetically favorable. So at this point, carbon atom thinks, okay, I have oxygen here. Oxygen tries to pull electrons towards him. So he says, okay, oxygen, you want my electrons so badly, take them. So one of the electrons, you see a double bond here, so this is a sigma bond and a pi bond. So pi bond is basically broken, and electron pair, so you remember, so one such line is a pair of electrons, goes to the oxygen, and it basically acquires a minus charge. So he gets its 8 electrons. If you did the homeworks and you draw all that bonding, non-bonding pairs and so on, you are probably able to draw the things. And we have this sort of intermediate that is called a tetrahedral intermediate, because this carbon atom is tetrahedral. Now, how that looks like? So let's take a look. So these electrons will be used to create a new bond. Electrons from one of these bonds, from the pi bond basically, will move to the oxygen. Let's check. So you see what happens. A new bond is created and electrons go here. So now oxygen has acquired minus charge, it's drawn here as a minus, and nitrogen has acquired a plus charge. This reaction is a bit more complicated than some different reactions, but I just didn't find anything better. So at this point, a transfer of a proton happens. Here you see these arrows, so let's take a look at that. So here you see a proton transferred from the nitrogen to the oxygen. So we get an OH group here, and we have an H2 group here. What happens next? We have a tetrahedral intermediate, and what happens at these sort of reactions when you attack the carbonyl group often happens. It's a formation of the tetrahedral intermediate, and then one of the groups is leaving. So it will be our leaving group. I'll tell you a bit more in details how do we decide which one leaves, or at least we can get a hunch. But let's take a look here. So once again, a non-bonding electron pair, you see this arrow showing here. It will create one more bond from carbon to nitrogen, so we will get a double bond. And carbon will reject one of its electrons that were bonding, and they will go to the chlorine, basically creating a chlorine anion. So chlorine will go away. That's a leaving group. Let's take a look how that works. So you see this bond to chlorine has broken, and here we created a double bond. Now chlorine leaves with the minus charge, so he took electrons, bonding electrons with him, and is going away. It's like that song. I don't know why she's leaving and where she's gonna go. I think she's got a reason, but I just don't want to know, and that's a leaving group. But we want to know reasons because we want to do some chemistry. Great, and now we have some plus charge on the nitrogen, and we may expect that something will change in this molecule, and basically a hydrogen is leaving as well. So now you see that these electrons will go to recreate a double bond with the oxygen. One of these bonds will be broken, so you see once again this arrow, so they will go to the nitrogen, so this arrow, and nitrogen will acquire no charge, so now it's positively charged because it used its electrons from the non-bonding pair to create a bond, and now he will take them away and become electrically neutral. And here how that looks like. So hydrogen is leaving, this double bond reformed, and here we have it. So that's basically a nucleophilic substitution at the carbonyl atom. Yes, very good question. Why chlorine leaves but not, let's say, this ring? That's a perfect question, and let me show you exactly why that happens. This is just terminology, just that we call these sort of things like acyl chlorides, acids and anhydrides, esters and amides. So nothing interesting here. Here is once again this reaction. So you see a nucleophile attacks this carbon atom, creates a tetrahedral intermediate, and then something leaves. Now let's get to the question what leaves and why it leaves. The thing is that whatever is leaving, let's put it that way. The group that is leaving should feel herself comfortably without the rest of the molecule. We had a very similar situation when we considered on the lecture in the lecture 3 different acids and bases. So you remember that there are certain acids that can, let's say, throw away a proton and they feel comfortably without that proton. That means that these sort of anions are stable, at least in the in water, so in the solution, and they feel, let's say, pretty comfortable. Very similar principle can be applied here. So if some of the groups is going to leave, it should be stable on her own. So it should be, in some sense, it should be willing to leave. As a guideline to who will leave, we can use the same thing as pKa. So here is a pKa of the acid that can be created with the help of the leaving group. So what kind of acids do we have here? So with the chlorine we have H-chlor. With the methyl group we have just simple methyl, so CH4, and with the and here we have a simple ethanol, yeah, so we have ethyl OH. Now let's consider if any of these groups is leaving. That's basically what we should get from here: chlorine minus, CH3 minus, or ethanol, well, or ethane O minus. And now how stable are they? This stability can be described in terms of pKa. Now tell me, what does it mean? So if pKa is high, very high, does it mean that the group is quite stable in the solution, or does it mean the opposite, it is quite unstable?
Unstable.
I'm sorry, I didn't hear.
That means it's more unstable in solution?
Yes, that means that this group is unstable. So the higher the pKa, the more it wants to keep the proton. The more it wants to keep the proton, the less stable it is without that proton. So you need to find the group with the lowest pKa. And if you look at this table, you see that that methyl group has a very high pKa. So probably you will never find something like CH3 minus anywhere. So that's impossible. At least in water, it will just get some proton from the water and transform into CH4, so you'll never observe that. 16 is quite high pKa as well, while chlorine has pKa minus 7, which means it is quite comfortable to exist as this sort of anion, so as a chlorine minus. So this is the case. So you can use pKa's as the guideline to the stability of the living groups. The lower the pKa, the more living group is stable, and the more it is stable, the easier it is for this group to leave from the tetrahedral intermediate when this double bond is reformed. So that's the case. Here's one more example. You see this sort of anhydride. Once again, we have not even one but two carbon atoms that have a partially plus charge, because these oxygens, they are trying to pull electrons towards themselves. So here we have that. So one of them can be attacked, a tetrahedral intermediate is formed, and once again we ask ourselves, so what is the living group? Who from these three options who will leave? And we can use once again pKa as a guideline. So we have methyl group, pKa 50, well, not probable. We have OR group, something like this one, pKa quite high, so not very likely. But we have this sort of group that is some sort of, well, that's basically acetic acid. So acetic acid is this one. And we see that it has pKa 5, so probably that's what will leave. So acetic acid leaves, or let's say conjugated base to the acetic acid, and here is what is left. Okay, this part more or less clear, I hope. Good. Here's one again, some sort of table that shows us pKa's and thus living group abilities. So increasing living group ability goes with decreasing pKa. So pKa grows this way, group abilities to live grow this way. Few more reactions. So once again we have partially positively charged carbon atom. We attack that with this sort is some sort of salt that has dissociated, so we have minus charge here, so it likes to attack partially positively charged carbon atom. We have once again a tetrahedral intermediate, and once again we are checking these groups and deciding who will leave. So this is sort of formic acid, so it will happily leave as well, but we have chlorine here that has much lower pKa, so probably chlorine will win and chlorine will leave, forming something like this. So that's what we have. Okay, some more samples, but I think I will skip that. So here is just one more reminder. So this reaction to go, we should have, so X should be a good living group, at least it should be better than anything else. If you are trying to connect some Y and Y is better living group than X, it probably will leave. So maybe reaction will go, but initial reactant will reform at the result and you won't get any product you wish. Y must be strong enough nucleophile to attack this carbon atom, so you may have nucleophile but it's not strong enough, and it should be good enough electrophile to react with the Y. And of course, in general, the higher the pKa, the better is the nucleophile. Okay, there are certain other factors that are important, so I will not spend time on this. I just wanted to show you that we may have not only pooling electrons due to some sort of electronegativity, but we may have, at the same time, we may have some partial donation of electrons due to the resonance. So you see these sort of different chemicals here, and it turns out that these oxygen or these oxygen or nitrogen, they can a little bit donate electrons due to so-called resonance effects. So here it's nicely shown that you have this non-bonding pair on the nitrogen, and it can be partially charged with the anti-bonding pi orbital of the CO bond, and thus carbon becomes a little bit less positive, so it a bit compensates the effect of pooling electrons. So it becomes harder to react with the nucleophiles. So you see that with the chlorine, when you have no resonance, it goes pretty fast at 20 degrees Celsius. When you get some groups that are a little bit better at donating electrons, you first get your reaction slower at 20 degrees C, or you need some heating with the catalyst, or you need a very prolonged heating with the catalyst. Nitrogen is much better at donating these sort of electrons because its electron pair is higher in energy, so it's better donated. But let's keep these. Yeah, one more notion. It may happen that nucleophilic substitution may lead to the loss of the original oxygen atom. So double bond is reformed, but the original oxygen atom is lost. You can track that if you use different isotopes for the oxygen. So here you see oxygen 16 and oxygen 18 are used, and you see that the reaction goes, and this oxygen is swapped by the different oxygen that comes from water. Good. Here is one more quite complicated reaction that goes, let's say, to the hemiacetal. I'm not sure if we will consider that. How much time do we have? Okay, let me show you it in this form of 3D, and we call it a day. Here it is. So this is acetaldehyde. So you see, if we had OH here, that would be acetic acid, and now we have acetaldehyde. And here is one more interesting option. If we have acidic conditions, so you have added some different acid that provides a lot of protons, this oxygen can be protonated. So it can use one of its non-bonding electron pairs to create bond to the hydrogen and acquires a partial positive charge. Let's look at that. This is the reason why quite often some acids are used as catalysts in these sort of reactions. So now what we see here, so once again we have these we have attack. So this carbon atom, it was partially positive due to oxygen pulling electrons towards. Now oxygen has acquired a positive charge, which means that this carbon atom became even more positive. So now it's a really good target for a nucleophilic attack. And here we have that methanol. I guess it's methanol. So we have methanol. We have oxygen atom with that non-bonding electron pair, and it's trying to attack this atom. So let's look what happens. A new bond is created, and electron from this double bond goes to this oxygen. This oxygen now acquires no charge, so it was positively charged, now it's neutral. That's great. We have OH group, and now we have attached this group to our molecule, but now we have oxygen once again with positive charge. And it may happen that this hydrogen is now willing to leave. So if we check all that pKa's, so on and so forth, it may be a good idea for him to leave. So he will just reject electrons for the sake of the oxygen. This bond will be broken, oxygen will become neutral, and hydrogen just leaves. So here we have it. And here is a hemiacetal that is formed in these sort of conditions. There is a set of other reactions here, but since we are so scarce on time, I guess I'll just skip that and we get to whatever we have next. Okay, and what we have next? Next we have SN1 reactions. Didn't I forget to say something in here? I guess no, nothing. Okay, there are two interesting types of substitution reactions. One is called SN1, the other is called SN2. S comes from substitution, N comes from nucleophilic, and the number comes from the order of the reaction. We will get into that orders in the fifth lecture, so maybe I will just hand-wavingly say something and we'll skip that until the fifth lecture. Okay, so different reactions, they may, depending on the mechanism of the reaction, you will see that if you measure the concentration of the reagents and the rate of the reaction, so how fast the products are formed, you will see different laws, and it turns out that there is one case, for example, so some substitution reactions are sensitive to the concentration of both the substrate and the nucleophile. So you add more substrate, you get a higher rate of forming of the products. You add more nucleophile and your rate grows once again. So for example, these say they grow linearly. But there are some other reactions that only depend on the concentration of the substrate. So you have substrate, you add more substrate, you get higher rate, but you add more nucleophile and reaction rate does not change. And there are a few other subtleties with respect to the stereoisomers. So some reactions, they generate specific stereoisomers, so they are stereo selective, or they do not, and they generate some sort of mixture. And this is the time to get, let's say, some understanding which reaction is which. So SN1 reactions, so this is the SN1 mechanism. It involves two steps. So the first step is a really slow step. So at some conditions, a bond between the carbon atom and a living group can be broken, and the living group just goes away. It may sound strange, but wait, in the third lecture we saw the same mechanism with respect to protons. So all acids were happy to throw away a proton, and what's left, that's left. This is quite similar situation. When living group leaves, we basically are left with the carbon atom that has a positive charge. So positively charged carbon with just 3 bonds is the perfect target for a nucleophile. So a nucleophile comes by, sees this sort of carbon atom, says, "Way, it's a great target," and creates a new bond. So here we have our carbon atom with the nucleophile attached. So 2 steps. What about the rate? Can anyone tell me why this reaction does not depend on the concentration of the nucleophile and just depends on the concentration of the of our reactant? So the key is here. So one step is very slow, the other step is quite fast. Enzyme, no, it's there are no enzymes here, so we are just working at the moment we are working in flask with some sort of chemical, just adding and rejecting them. So here is a very simple logic. So you have a two-step reaction. So the first step is very slow, the second step is very quick. So I'm not sure how to say how to do that. Maybe, I don't know, you can think of something that works in two steps. Let's say cooking something and then distributing that. So if the step of cooking is quite long, so you spend an hour to do something, and then you distribute that in a matter of minutes. So here is a very similar situation. So the second step is quite fast. So if you have this sort of carbocation intermediate, you immediately get the product. The problem is the first step, so you should wait until this leaving group leaves. So basically the overall speed of the reaction is the speed of this slow first step. At the moment it leaves, you almost certainly will find some nucleophile, it will immediately react and you get the result. So you should wait for this step. So that's why if you increase the concentration of this reactant, you have a higher rate of formation of the product because there are much more molecules and there is much more probability to find one of them with the leaving group detached. But adding more nucleophile will not help you. The amount you have already is capable of basically reacting with all the carbocations you have, because carbocations are scarce. Nucleophile is plenty, so you don't you don't need any more of that. So that's why you get rate of the reaction that is independent on the concentration of the nucleophile. Is this more or less clear? You can think it this way. Suppose we have two steps. So the first step is, I don't know, asking you a question during exam. So I'm asking, you're answering. That takes it takes a lot of time. And there is a second step when I don't know, I take some sort of form. I write mark there. So I write your grade there, and I put my signature. So the second step of putting signature is really quick. So at the moment you have answered and we understood what grade you have, just writing down that it's nothing. So basically, if you ask how long does it take to pass an exam, you will most certainly look at the first step, the slow step. So how much time do we need to get through all the questions, to get the answers, so on and so forth. And the second step, writing down and putting signature, that's
Привіт.
nothing.
Ну, ти написав, ми це не зробили. Це ще не зробили.
Ну, я чуть-чуть не понял, или мы это зробили, или як. Ну, это как видео добавить надо.
Где?
Any questions?
Я правильно прочитал?
А где ты это прочитал?
Ну, перечитай.
Можешь пошарить?
Ну, перечитай.
Что...
Она скипала. Да, конечно, смотри, все вот.
Пошарить, так быстрее будет, потому что ты уже знаешь, где я.
Alona, please,
Вот,
I guess
смотри.
you didn't turn
Вот,
off
смотри.
the mic.
Вот это додали, потом I'm шарим на видео, тра-та-та, потом на всяк выбор. А потом она еще сделала. Будь ласка, це на кейс-так.
Okay, let it
И Google
be.
Drive.
Що вона
И Google Drive. Открывай Google Drive.
Okay, let it be this way. Good. So, what about any comments regarding reaction?
Не
So,
знаю.
is it clear more or less why do
Короче, я
we
тоже
have
не, это надо
this sort
прописать,
of
мы
rate?
просто автоматизировать, чтобы, ну, я отметил, что завтра, если что, уже там, или сегодня напишем еще. Так что,
Ты
лучше все это,
послання на відео selector файл вон.
No, I can't.
Давайте,
I
будь
don't
ласка.
have such
Наверное,
ability.
кейс-стаді, то, що ми писали.
Only I'm not the host, I guess.
І...
So I'm afraid I can't.
Нічого.
Okay. It's like
В тому документике, що я писала, там електрофайла нету.
то есть туда добавить электрофайл?
Ну, я так понимаю, туда. Не знаю.
А ссылка на...
Okay, so something
Просто на...
no good
на
with this
відео,
lecture.
да.
Я подумал, что надо электрофайл добавить.
Альона, у
Лучше
вас
це
вімкнений
спросити у
мікрофон.
Світлани, да?
Можете його, будь ласка, вимкнути?
Да, лучше ты спросить.
Альона?
Ты не в курсе, там Светлана в конце места делила.
Окей.
Yeah.
I tried.
Yeah, at least we tried.
Я не знаю вообще.
so-
Ничего насчет этого.
Ну, я просто надо как-то направила,
Good.
осталось, потому что сейчас нету, там, ожидаем там через 2-3 дня. Тут ничего не пишет, я как-то тоже думаю, что это.
Okay, let's look nice graphics and
Там
just
просто как-то
disregard
прочитали, что-то.
everything else.
И поэтому.
So here is one more reaction. So this is SN1 reaction. Once again, the first step is the leaving of the leaving
Ну все,
group.
я вот это увидел.
So here we see a good leaving group. It's a chlorine,
Как я понял, это видео
and
надо добавить.
electrons from the bond, they can move to the
Я
chlorine,
так.
and
Мне
well,
кажется,
you will
что это
create
надо
a
вписать
chlorine
в это.
anion.
Напиши, это надо вписать в нашу эту или в
So here, how that looks like in
Она
3D.
ответит, как
Так,
сможет.
хорошо.
То я думаю,
Let's look at that.
а я что-то
So
подумала,
this
что
group is
Дима
leaving.
что-то не сделал. Думаю.
This is the slow
Я ж
step.
не открывала, я
So
сразу
if
думаю,
we
сейчас
have
давай
some
выясним,
amount
потому
of
что
this chemical,
будут
we should
смотреть, открывать.
wait for maybe for a long time before this chlorine leaves. So at the moment it leaves, we have a really nice reactive compound that has a plus charge on the carbon atom, and this carbon atom can be attacked with the nucleophile. Let's look at that. So here's our nucleophile. So here we have S atom, so a sulfur atom, and it has some minus charge, so probably it was some sort of HS, and hydrogen,
Алло,
well, proton
нормально,
was
всё
lost.
нормально.
Зрозуміло, треба додати ці відео в кейс
So
стаді
let's
ліпками.
look how that bond is formed.
Як?
So here that happened.
Ну, не
So
зрозуміло
leaving
взагалі,
group
що
left as the
Це
first step.
додати
As
просто
a
в
second
файл
step,
кейс
we
стаді
have
оцей,
the
що
addition of
ви
the
сьогодні
nucleophile
створили
that
в
created
додку.
a new bond.
Чи це
And
треба
here is
в
our new chemical.
електрофайл з гівками, чи що треба?
Так, непонятно, що куди добавляти.
Okay.
Ну да.
Okay, so hopefully that's
хорошо тогда.
more or less.
А то я тут виключила звук, щоб з тобою поговорити.
Все, нажимай, все, давай.
No, you didn't turn off the
Давай.
sound, so.
Давай, та не за що. Пока. Якщо що, пиши. Пока.
Okay. Okay, so here we have it. So here is the result of the reaction, and we have our new chemical. Good. So I hope it's more or less clear what happened. So does anyone have any comments or questions so far? Good. Regarding the previous question, is it more or less clear why when we have the first slow step and then some number of fast steps, it may be here it's one, but it may be more than that in other cases, we are always looking at the slow step, and that will be a rate determining step. So is it clear, more or less? Omnious silence. Okay. I really hope that it is, because that's basically the point of this lecture. Now, what else? Stereo specificity, or I have some better slide here. Comparison SN1, SN. Okay, let's immediately compare that to SN2 reaction. That will be great, and then then I'll tell you about the stereo specificity. You see, or no, I'll tell you now. Okay, you see what's going on with this carbon atom. It has 4 substituents, and it may happen that these substituents will be different. So I will have some sort of R1 here, some R2 here, and some R3 here. So what does it mean for this carbon atom to have 4 different substituents?
It means it has no free electrons.
No, no, no. Remember your homework. It's chiral. It's chiral. So you may have different isomers of this chemical. So you remember all that images with the mirror and the mirror image and so on and so forth. So that's a reminder for you. It's chiral. And when we have SN1 reaction, a leaving group leaves. So this is the case. So a leaving group has left. And now what we have, R1 here, R2 here, and R3 here. And now returning to our second lecture on the structures, on the 3D structures. What do you expect the thing to have, what kind of structure do you expect here in 3D? In the vicinity of this carbon atom? So what do you expect? Yes, absolutely correct. It will be planar. So here we expect a tetrahedral structure. It has 4 substituents, it's tetrahedral, and it's chiral. In this case, when the group left, we have a planar structure. So now, when the nucleophile comes by, it may attack from below of this plane or from the above of this plane. And you will get 2 different chemicals with different stereochemistry, depending on where we have this sort of attack, from the above or from below. So that's why SN1 reactions, they will create you a mixture, probably a racemic mixture of different chemicals. Good, here is comparison, maybe. No, let me say a few words more about SN1, and then we will move to SN2 reaction. I'm trying to get in time. Okay, so I already told you that SN1 reaction basically strongly depends on the first step, so losing of the leaving group. So we get a better oh, thank you. Good. So we can get better reaction when whatever is left. So when the leaving group left, so we have something after leaving of the leaving group, and if that something is more stable, it means that there are more chances for the leaving group to go. So the same reasoning we had for acids and bases. So I told you that's, I don't know, it's some sort of common sense. So if you can, so you can happily give something away if you are stable without it, if you can exist without it. The same thing was with acids. So if that conjugated base was happy without the proton, it was stable, and the acid was strong acid because it was happily donating that proton. Here is the same situation. If you can live without that leaving group, if you're stable, great, then you are okay with throwing that group away and undergoing SN1 reaction. So here's what we have. The stability is defined by the fact how good can you stabilize that positive charge. The more well, these molecules, they don't like if you have a lot of charge in one place. So if it is concentrated, you probably get something unstable. So the more you are able to delocalize positive charge that you get after leaving of the leaving group, the more stable thing you get. This is some sort of intermediate state. So here are different carbocations, and here is exactly methyl carbocation, and you have this positive charge, and it is very, very unstable. So you remember that pKa is just over the moon, so it's 50 or something like that. If you have one substituent, so you have one more carbon atom here, you have some sort of delocalize this positive charge just a little bit, but it is more stable than when we had no other carbon atoms nearby. If we have two substituents, it's even better. So you can see here these images, they show you the distribution of charge. So here a negative charge is strongly, it's just on the carbon atom, so it's very unstable. Here you see that this charge is some sort of smeared, so it's delocalized. Here it is even more delocalized. And if you have three substituents, it's even more delocalized. So the more substituents you have, the better you can delocalize the positive charge. So the more stable carbocation you get, and the more SN reactive substance you will have. So that's it. So the more substituents, the more stable carbocation, the more SN1 reactive. So that's the simple logic that we have here. Here is one more slide with this sort of hyperconjugation. It involves a electron delocalization via partial orbital overlap from a field bonding orbital to an adjacent unfilled orbital. And here are some images that show you this overlap between orbitals. So here we have some sort of vacant p orbital. So this is our carbon atom with the plus charge. So it has lost its leaving group. Now it has this plus charge. It means that it has vacant p orbital, so there is no electron to use that orbital. And it looks, as you see, it looks quite planar. And this vacant orbital can interact with electrons from other p orbitals that are filled, for example, of these carbon atom. The more such carbon atoms nearby you have, the more you can alleviate the problem of the overwhelming positive charge on these carbon atom. And here are examples. So this is third butyl cation, so it is most stable. It is more stable than isopropyl cation, so here it is. So you have just two substituents, just two nearby carbon atoms. You see they all acquire some partial plus charge. It is more stable than if you have just one substituent and two carbon atoms acquire plus charge, and is more stable than this sort of methyl cation. So it is least stable. So here we have it, and I guess you will have something for the homework to determine which structure is better SN1 reactant, so that's the logic you should follow. So count how much substituents you have. Okay, so here is reaction of SN1, and this is about the stereochemistry. This is step 1, so bromine goes away, the leaving group. So H-brom is good acid, so you may guess it has some good pKa and is happy to leave. Here we have this flat molecule. So this flat carbocation. And now you see that nucleophile may attack from above or from the below. If it attacks from above, you get this chemical. If it attacks from below, you get this chemical. And since you have 4 different substituents on this carbon atom, you have basically a racemic mixture of 2 different isomers. So that's what you have. Okay. Here is one more example. I guess we skip this a little bit. One more stereochemistry example. So once again, here you have water attacking from above or from the below. So you see this empty p orbital. So it is basically these electrons are interacting with that p orbital to create a new bond. So that's what's happening. So that's why we were paying so much attention to all that orbitals and so on. And here you have S-sec-butanol and R-sec-butanol. So these are 2 different enantiomers of these molecule. Good. What's that? Okay, I'll skip this for a moment. That's once again about stability, so I hope that was more or less clear. Let's skip to the SN2 reaction. So that's nucleophilic substitution, order 2. What changes? Well, there is a different mechanism. This mechanism involves nucleophile attack and leaving of the leaving group at the same moment. So you see a nucleophile attacks with some electron pair, empty, sigma star, so it's anti-bonding orbital. It should attack from the behind of the leaving group. I hope you remember what happens when we put electrons both on the bonding and the anti-bonding orbital. So it looks like no gain in energy. So putting his electrons in this anti-bonding orbital, it creates the case when any of them may leave. And it turns out that in some cases it is much better for the leaving group to leave. For example, it has some, I don't know, better pKa, so lower pKa, and it feels much happier without the rest of the molecule than, let's say, this nucleophile. And that is performed at exactly the same time. The rate of this reaction will now depend on both concentration of the nucleophile and concentration of the chemical we are attacking. Why? Because in the first case of SN1, we had we had 2 steps. First step was slow, and that step involved only our substance. Here we have involved 2 different chemicals in one step. So you can recall some similar formula from the lecture number 3 when we had hydrogens and conjugated bases. And here is basically the formula for the rate. So if 2 molecules collide, so they collide, that should be the exact species of the molecule that we want. So the probability that this one is, for example, our substrate, is the concentration of the substrate, or let's say it's proportional to that concentration, whatever, and that this one is the nucleophile is proportional to the concentration of the nucleophile, and here we have just hidden away all other parameters, so they should move with appropriate speeds, they should be appropriately positioned in space, so you should attack with these electrons this orbital and nowhere else, and so on and so forth. But anyway, you see this product, so you get the rate that is dependent on both concentration of these the substrate and concentration of the nucleophile. Good. What else I wanted? Do you see any, let's say, hidden problem with this attack? What if I engineer some molecule that has, I don't know, some sort of antlers here, so lots and lots of large groups that are all over the space. How do you think? Will it be more or less reactive in the sense of SN2 reactions? You should think from the point of view that this nucleophile, think this is a reaction when two molecules should hit each other. You should and moreover they should hit in a certain way, so you should place the electrons on this anti-bonding orbital. You should think from the point of view, is it easier or not to get to this point? Less reactive. Yes, absolutely correct. It will be less reactive because it's more complicated for this nucleophile to get to the place of the reaction. It's called sterical hindrance. So the more sterically hindered is this place, the more complicated will be for the nucleophile to get to there and start the reaction. So that's why if you have no sterical hindrance, let's look at this one. So we have leaving group and CH3. Hydrogens and protons, they are small, so what can they hinder? It's perfect for the SN2 reaction. So the nucleophile has full access to this anti-bonding orbital and there is no problem to react. If we have some primary carbon atom, so there is something is substitute, well, it's a little bit more complicated to get there. You still can have SN2 reaction, but it's a bit more complicated, it will be slower. If you have carbon atom with two substituents, it's even more slower and it's, let's say, not so probable to have SN2 reaction. And with three substituents, I suppose you will get no SN2 reaction at all. So probably it's not. So you can see that SN1 and SN2 reactions are in some sense opposites in this case. So for SN1 reaction, it was beneficial to have more substituents. Why? Because after the leaving group left, we had positive charge and we needed something to delocalize that charge. They don't like to have a lot of charge in one place, so we need to delocalize it. In case of SN2 reaction, you have very different mechanism. You don't wait for some leaving group to leave. It will leave when a nucleophile hits this molecule. But for that hit to happen and in exactly that place that we need for them to hit, we need to have less sterical hindrance, because if there is some obstacle, it will just can't get through that obstacle and put its electrons in that anti-bonding orbital. So that's what we have. Okay, let me check. What do we have? Okay, we have something like 15 minutes. I want to show you. Okay, let me show you some nice some nice mechanism. Let's check this one. let me show you some nice pictures. And okay, so here you see a reaction. So this is a bromine and anion, and here you see a methyl chloride. And what happens here? So chlorine will leave, and bromine and it will be substituted by the bromine. But what should bromine do? It should attack from the correct angle, so it should attack from this side. Why? Because here you have sigma bonding orbital, and here you have sigma anti-bonding orbital. So it should place its electrons in here into sigma star orbital, so anti-bonding orbital. Let's look how that works. So here it comes. Did you notice anything interesting? What happened to the protons? Let me show you
They
once.
rearranged.
Yeah, they like inverted. Yeah. So here what happens, and it's quite interesting from the point of view. What if instead of just 3 hydrogens, we will have, well, some different groups, maybe 1 hydrogen and 2 groups. What will be with some sort of stereomers or stereoisomers in this case? We will generate one specific isomer. So in case of SN1 reaction, we generated few different isomers. Here we can generate one specific isomer. Here's one more image that I like. Here is the energy diagram for the SN2 reaction. So we will talk a little bit more about that in the lecture 5, so I'm not going into lots of details, but you see it goes through the intermediate state when this bond is partially formed and this bond is partially broken. Here you see a video of this happening. So OH attacks some molecule and one atom leaves. So and here you see what happens to the orbitals. So nucleophile puts its electrons on the anti-bonding sigma orbital. Here you have some intermediate state. If we go through that state, we have nucleophile attached to the molecule. Let me search. Okay, there are certain cases when both mechanisms are possible. So it may be that there is some chemicals where leaving group may go first, and then you have nucleophile attack, or when you have nucleophile attack and leaving group leaves at the same time. Here is some sort of table that tells you what is more likely to happen, SN1 or SN2 reaction. So here we have a structure, so X is the leaving group, and you see that there is no chance for the SN1 reaction. Why? Who can tell me? When X leaves, what are we left with? No. When X leaves, we leave with the methyl cation. It is very, very unstable because there is nowhere to delocalize positive charge. So it will be probably not formed and X will probably never leave. So you cannot get SN1 reaction because your leaving group cannot leave. What about SN2 reaction? It's really good for SN2 reaction. Why? Because you have no sterical hindrance. It's nothing for the nucleophile to get through 3 hydrogen atoms. They are small and there is no hindrance, so it's pretty okay. What about primary? So we will probably still get no SN1 reaction because there is still not enough carbon atoms to delocalize positive charge. Maybe in some cases, but probably not. And it is still good for the SN2 reaction. There is almost no hindrance once again, so there is a bit more than in this case, so it's worse of the SN2 reactant, but still okay. For the secondary structure, we can get both reactions. It is already good enough for the delocalization of the positive charge, so you can expect for the X to leave, and you will get more or less stable carbocation, and it is still not so hindered so that nucleophile cannot get through, so you can still have SN2 reaction. So your nucleophile can still get through. If you have tertiary structure, that's good. That's good for the SN1 reaction, because when X leaves, you have lots of carbon atoms, so you can delocalize your positive charge, and that's pretty okay. But you will probably have no SN2 reaction because it is quite sterically hindered. So your nucleophile just will not be able to squeeze in between these groups to get to that carbon atom. So that's the general logic of what we have. So SN1 reaction, your leaving group must be good to leave, so what is left behind should be good at the delocalizing the positive charge. That's great. For the SN2 reaction, you should have this carbon atom available so that nucleophile can attack it. Okay, and for the few last moments, I guess we're almost there. That's good. That's really good. So here are once again these two mechanisms, SN1 and SN2. So SN1, rate determining step, leaving group left. The second step, fast step, nucleophile attaches. SN2 reaction, nucleophile attacks and at the same time rejects the leaving group. What does it say? So we have different nucleophiles. So weak nucleophiles, they tend to react with SN2 mechanism. Why? Because after leaving group left, you have much more potent electrophile. You have a positive charge on that carbon atom, not just some sort of partial positive charge, but a really large positive charge. So it's easier to react. So weak nucleophiles will tend to react with SN2, while strong nucleophiles, they will tend to react with weak with SN1, while strong nucleophiles will tend to react with SN2. Because they are strong, though, so they can just take that carbon atoms for themselves. Of course, if they can get to that carbon atom, anything may happen. And here are some rates of different reaction, and we can see the changeover from the SN1 to SN2 in the reactions of a single compound if we choose one that is good as both mechanisms, such as benzyl sulfonium salt. Both mechanisms are available for these compounds, and we can use some weak and some strong nucleophiles to see what changes when we have different mechanisms. So here you see SN1, we have rates of the reaction for 3 different nucleophiles. You see they are almost the same. Why? Probably one of the last questions for today. Who can tell me why they have the same rate despite these are pretty different nucleophiles? Reaction goes through SN1. That's a very big hint for you.
Because we have like very long rate determining step when something should detach first, and so it affects the rate the most.
Yes, absolutely correct. So the longest part of this reaction is the first step when the leaving group goes away. Since we are reacting with the same chemical, so all these nucleophiles are reacting with the same chemical, of course we expect that first step to take the same amount of time. Because that depends on this chemical, it does not depend on the nucleophile. So that's why this rate is basically a description how long does it take for this chemical to reject the leaving group. And this chemical is the same in all the reactions. So of course we get the same number. But what happens when we switch to the SN2 reaction? Here we have pretty different numbers depending on the nucleophile. Why? Because there is a different mechanism. So your nucleophile should attack that carbon atom, and now the rate of the reaction will depend not only on the chemical we have, but also a nucleophile is involved. So we will probably get different numbers depending on the potency on that nucleophile. So that's what we have. And here you see some more reactions that go through SN2, and here are some more numbers. Okay, what's that? These are some sort of more examples of SN2 and some sort of orbitals, but I don't think we have time for that. Just will show you on the last minute the SN2 reaction in the biochemistry. So you see that here are some chemicals that here is nicotine that is produced by certain certain plants, and here we have adrenaline and choline. So choline, you can meet that in some brain in form of acetylcholine and adrenaline. So so choline is important in the transmission of nerve impulses, and adrenaline causes blood pressure to increase. So these are pretty interesting chemicals, and here you see an example of a synthesis that uses the mechanisms that we have studied. So here is a triphosphate group, this is adenosine, and basically this is ATP, and here we have methionine attacking this ATP. So we have adenylyl methionine and triphosphate ion. So here we have SN2 reaction, and here is one more reaction. So this adenylyl methionine reacts with dimethyl aminoethanol. So here is the reaction. Once more you see this non-bonding electron pair used to create bond here, and these electrons they go to the sulfur atom, and and here what we have. So we get choline and we get some sort of leftover. The thing is that when nucleophile attacks, in this case as adenylyl methionine, we see that attack takes place at the less hindered CH3 group rather than some of the more hindered CH2 groups. So you see that this S has partially positive charge, so this charge will probably affect, for example, this CH2 group, and we may have expected attack at this group, but it is sterically hindered because this is SN2 reaction. So we should get a hit between these two molecules, and this one just can't get there because you see it has all these antlers. and it just cannot get through all these. So it prefers to attack this CH3 group that is much less hindered and more easy to access. Okay, I guess I have used all the time I had. So maybe if you have any questions, please. I guess we were able to get what I wanted, so we have gotten through SN1 and SN2 reactions, so you probably now will be able to solve the homework. So maybe next time we will proceed with another topic to not mix everything up, and I will integrate some parts of this lecture into there, so we will somehow alleviate our lost lecture. Good, so maybe some questions, comments, please. Okay, nothing. Okay, I hope that you liked all these arrow things and all these 3D stuff. Maybe we will get more of that in the next lectures, I hope. So so good. If no questions, no comments, then have a nice evening and see you, I guess, next week on Tuesday.